is indeed an outstanding personality in the field of materials, and I would just like to highlight the main goals that he reached at the level of micro and nanotechnologies. I have to say, first of all, the control of size and luminescence properties of semiconductor nanostructures, synthesized by reactive laser ablation, the development of new experimental tools, and the comparisons with simulations so as to gain atomic scale insights into the surface process that govern nucleation growth and assembly, and the formulation of new strategies for synthesizing multifunctional nanoscale materials to be used for electronics and photovoltaics. This is for us a great privilege to have you among us as a ward of Blaise Pascal, but also as a member of our academy. Maybe a photo?
Thank you very much. It's a great honor and a privilege for me to be here with you today. I'm extremely grateful to the Academy for recognizing the work we've been doing. And in fact, I'll start by acknowledging, of course, the funding sources that support us from the provincial government in Quebec and the federal government of Canada and other entities. And then collaborators worldwide, many of them in Europe, of course, as well as current and former students and postdocs. These are the new young generation that actually does all the work and deserves all the credit. I should mention that you're all welcome to visit us in Montreal. You should be aware that we have only 2 seasons, the winter and the construction season. And in the construction season, it's warm enough that we can organize a water fight in the backyard. So we don't wear ties for this occasion. If you visit during the winter, it's more likely to be a snow fight, of course. In fact, I'll mention briefly, perhaps what I'm most proud of is that I've been a professor 17 years, and 18 former group members are themselves professors in 10 different countries. I also wanted to mention very briefly this course that I developed, which then turned into a book that I co-authored, Survival Skills for Scientists. It's a professional development course for young scientists so that they will not repeat the same mistakes that we made in our careers. We also published a number of papers in the Journal of Materials Education, and the book was so successful it was even translated into Japanese. So you see there's a version of my book I can't even read. I have no idea if it's accurate or not. Okay, so now our work is in the area of nanoscale phenomena. We're interested in very small systems, a few nanometers to maybe tens of nanometers in size, which exhibit different behavior compared to the bulk counterparts. This is due to some quantum size effects because, of course, there's confinement of energy levels in such small volumes. There's also surface effects because in a nanomaterial, most atoms reside at the surface. And we're interested in using these nanoscale systems as building blocks for next generation technologies. Now, this slide lists the so-called 17 Sustainable Development Goals identified by the United Nations. There's one of them that I'm not even sure what it means. It's something like partnership for the goals, but anyway, it doesn't matter. I believe that energy is central to any form of development, and in particular sustainable development. So there's actually you'll find that there is some continuity with respect to the previous speaker. And what is sustainable development? In fact, I like to say that it's an oxymoron, maybe even with emphasis on the moron. The UN definition of sustainable development is meeting the needs of the present without compromising the ability of future generations to meet their own needs. Is that what we're doing? And this is a saying from North American ancient people. We do not inherit the earth from our ancestors. We borrow it from our children. This is the energy challenge, and this view graph is taken in part from the essay of my distinguished colleagues in Italy, The Future of Energy Supply, Challenges and Opportunities, in which they say, rightly, our generation will ultimately be defined by how we live up to the energy challenge. This is taken from Physics Today 12 years ago. It's still remarkably accurate. About 85% of the energy we use is based on fossil fuels. A few percent is nuclear, a couple of percent is hydroelectric, and everything else is kind of lumped in a generic category called biomass and other. Now, it's still early morning. I'm not sure if you've had your coffees, so I want to see if you're awake. I'm going to start asking you questions. There is one source of energy which is going to be crucial for humanity's long-term development on this planet, sustainable development. It's not labeled on this graph. Does anybody want to venture and say what it is? This source of energy that, yes? I would go more with solar. Wind power is, of course, very important as well.
Everything is come from the sun.
Yes, I'm talking about direct conversion of solar energy into another form. Of course, wind also relates to the sun. In fact, all sorts of energy on the planet, ultimately, even fossil fuels, it's decomposition of plants over millions of years due to solar radiation. That's fine. But I'm talking about direct conversion of solar energy into another form of energy. Does anybody know what is the percentage contribution of solar energy to the whole energy pie? Hint, it cannot be very high because it's not labeled on the graph. This lady over there says less than 1%. Gentleman over there says 5%. Gentleman is very optimistic. Sorry? 5. But this gentleman here also says 5. This one here shakes his head. Less than 1%, you agree with the lady. Does anybody offer more or less? Less? Gentleman over there is pessimistic. Okay. Most estimates are about 1%. On the other hand, we know that every hour the sun sends towards our planet enough energy to power the whole world for 1 year. Yeah? Did that get your attention? Every hour would be, in theory, sufficient for 1 year, but we only use 1% or less, right? So that's the bad news. The good news is that hopefully it can get better. From 1%, we can increase it a lot. There's one parameter of the sustainability equation that most people tend to neglect or don't want to think about. It's not really politically correct, but I studied science. I didn't study diplomacy, so I don't really care about being politically correct. And that's world population as a function of time. World population increases at a rate of 200,000 people per day. That means that in 1 year, you get 70 million people, new people, on the planet. Now, I live in Canada, so 70 million people is twice the population of Canada that pops up in 1 year, or twice the population of California. Now, if you wait 15 years, which is less than 1 generation, that's equivalent to the population of India that pops up on the planet. Less than 1 generation, you get the population of India, poof, popping up. If you go back in time, though, world population was much, much lower, and it was also growing very, very slowly until the 1800s. What happened in the 1800s? That's the era we refer to as the Industrial Revolution. Which fuel powered the Industrial Revolution? Coal. Now, that's the first fossil fuel that humanity used on a large scale. After that, we started using natural gas and oil. And in fact, the availability of these new sources of energy, at least on a large scale, drove this very steep increase in population over the last 200 years or so. We can call everything that happened since then the energy revolution because the lifestyle we are used to depends on the availability of these incredible sources of energy. We can say many bad things about fossil fuels. They pollute. They're not renewable, or at least on a timescale that matters to us. But they do have some advantages which makes them hard to displace by other technologies. One is that for a long time they were low cost, they're fairly easy to transport, and they have a very, very high energy density. As the previous speaker said, from a small volume of fossil fuels, you can harness a lot of power. And that's one of the reasons why it's so hard to displace them, including certain technologies. Like imagine a large-scale aircraft that wants to fly transatlantic. Today, you can only do it with fossil fuels. There's nothing else that will fly such a large jumbo jet across a very large distance. So we're trying to drive exponential growth based on finite resources, and since I believe 99%, or anyway, most of the people in this room have a training in science or engineering or related fields, you immediately appreciate that this is not sustainable. But suppose you want to convey this very message to somebody in your extended family or circle of friends who perhaps does not have such an advanced training. Well, what you can say is that one day we will run out of fossil fuels. It won't be today, and it won't happen overnight, but it will happen. And the day that it happens, we either have a replacement for that 85%, or we have to go back to the population level before fossil fuels, because that's what the planet can sustain without them. Of course, this is a doomsday scenario. Nobody likes to think in those terms. It is reality, nevertheless. Let me reassure you that this will not happen during the lifetime of anybody in this room. But remember what I said, we don't inherit the earth from our ancestors, we borrow it from our children. So what is the legacy we're leaving to future generations? Obviously, this is a much greater challenge than just scientific or technological. It's societal, political, economic, and so on. So I approached UNESCO, which is the United Nations Educational, Scientific, and Cultural Organization, which has a program called UNESCO Chairs. And in this program, you set up a network of participating organizations that will pool resources to address pressing challenges and contribute to societal development. In our case, of course, the UNESCO chair is on renewable energy technologies, and it's specifically dedicated to capacity building in developing countries. So the idea is that these networks and chairs act as think tanks and bridge builders between academia, local communities, research, and policymaking. Ideally, we want to inform policy decisions, and that, of course, depends on who's in power and whether they want to listen. By the way, as a side note, I count on your generosity. I'm collecting donations. We live in Canada, and I'm trying to get enough money to build a wall at our southern border. So please be generous. Please be understanding that we Canadians are victims of having this southern neighbor that is so obnoxious. Thank you very much. So the objective is sustainable energy for all. It's one of those 17 Sustainable Development Goals of the United Nations. We do it by hosting visiting professors and students, organizing international workshops and training, a small number of PhD students from developing countries. We have over 30 partner organizations in 15 or 16 developing countries. And the chair started in 2014. That was a magic year because it was the year we launched the chair. I was also elected as member of this academy, so it was a fantastic year for me. So what do we work on? We work on materials for energy saving. Saving energy is crucial to development. And of course, there's many ways of saving energy. One I won't talk about, but you can imagine is building materials, better infrastructure that will save energy for heating and cooling. What we work on is materials for light-emitting technologies. You may recall, 2014, the Nobel Prize in Physics was awarded to the 3 Japanese scientists who invented the blue light-emitting diode with high efficiency. Basically, each LED traffic light saves $1,200 worth of electricity per year, and lighting just one room in every house with LEDs reduces CO2 emissions by 1 billion tons per year. That's a lot. It's significant. So if you haven't invested in this technology, start thinking about it. Energy storage. So take renewable energy technologies. What is the challenge that is common to all renewable energy technologies? Storage, yes, because they're all intermittent. If you take wind, it goes in cycles of half an hour. If you take the sun, you have it during the day, during the night you have nothing. And even during the day, if a cloud passes overhead or a cloudy day, gray day like today in Madrid, you don't have a lot of power. So you need to store the excess energy. You know, you convert into electricity, but what do you do with that electricity if you don't use it right away? You need to store it for when you will actually use it later, right? I want you to appreciate another aspect that is not so obvious, but the best form of the best form of energy on this planet is actually electricity. It's the most ordered form of energy. Too bad that it does not exist in nature, except lightning bolts that we can't really capture and use their power. So we are struggling constantly in transforming one form of energy into electricity, either directly using it or storing it, and then converting it again, and each conversion process has an efficiency, so there's energy losses, so to speak, in every single process. And that's one of the key challenges. So you can see here, this is materials for energy storage. We have to increase the energy density and decrease the cost. In theory, we should be able to reach at some point 300 miles or 500 kilometers per charge so that we could be competitive with gasoline. Again, it's a matter of energy density. and that's difficult to do with current materials, current technologies. Yet again, imagine you want to fly a large aircraft across an ocean using battery power. Your battery would weigh 1,000 tons. Okay, 1,000 tons. So the plane wouldn't even be able to take off. It's a sort of thought experiment. Now, let's get to the point. This is the Earth at night from a satellite, and you can see that in the northern hemisphere we have a lot of energy available, and we also waste a lot of energy. And in the southern hemisphere, most people are not so fortunate. Now, Australia is not too bad because most people reside on the coast, and there's what you see, patches of light. This is the Amazon, aside from most of it having been burned recently, but anyway, there's not a lot of people living there, thankfully, I guess. Look at Africa. That's lots of parts of Central Asia. It's estimated that about 2 billion people do not have access to any form of energy. What we take for granted, electricity, and of course, as a consequence, health services and clean water, etc. There's about 2 billion people who have never experienced that in their whole lives. But we can look at this and invert it and call it a map of possibilities, because the same areas that are dark at night are the ones that have most sunshine during the day. So if we were to deploy solar technologies in these parts of the world, coupled, of course, with storage solutions, recall that in most of Africa, you don't even have an energy grid, so you can't even use the grid to sort of give and take energy. But anyway, if we were able to do that, we could actually implement societal change and development within 1 or 2 generations. So we work mostly on materials for energy conversion, also a little bit of energy saving and storage. The objective is to convert as many photons from the solar distribution into other usable forms of energy. And so this, of course, is the photosynthesis reaction, and similar to many others, the sort of prototypical case was Grätzel with dye-sensitized solar cells. We're trying to mimic the photosynthesis reaction in plants. And if you take the Grätzel cells, of course, the main advantages are the low cost and low energy intensive kind of technological fabrication. The major challenges are limited efficiency and stability. We decided to replace the dye molecule, which is a key component in that technology because it absorbs a lot of solar photons in the visible and infrared, with quantum dots. So these quantum dots are inorganic semiconductor nanocrystals, which are very small, nano-sized materials. And because of their size, by tuning sort of the radius or the diameter as well as the composition and the shape and so on, you can actually engineer the energy levels and the band gap. And so you can tune them so you can optimize the absorption of solar energy in certain ranges of the spectrum. Turns out that I have some concepts that are similar to the previous speaker. I also have the fuel cell bus in Iceland, so I won't dwell on that. What I would like to mention, though, is you're probably familiar with Jules Verne, the French science fiction writer who predicted that humans would reach the moon. And in The Mysterious Island over 100 years ago, he said, water will one day be employed as fuel. Hydrogen and oxygen, which constitute it, used singly or together, will furnish an inexhaustible source of heat and light of an intensity of which coal, that was the main fuel in those days, is not capable. Water will be the coal of the future. So there's 3 challenges in hydrogen. It turns out that the previous speaker works a lot on storage and production. We work mostly on production. The other key challenge is how to use it in a fuel cell, because the main catalytic material, electrocatalytic material, is platinum, which is rare and expensive. So that's another key challenge. So we work on hydrogen production. Where do we extract hydrogen? I mean, in the atmosphere, there's only about 1% hydrogen, so you can't really extract a lot from air. And on the Earth, it's always tied to other molecules. So the hydrogen that is combusted today in fuel cells, where does it come from? Anyone? Yes? Methane, CH4. Now, CH4, of course, if you burn it, you generate carbon emissions. So it's better to burn hydrogen or combust it, because then your only byproduct is water. But CH4 is still a non-renewable feedstock, right? So you're not addressing sustainability if you extract hydrogen from CH4. Where would we like to extract hydrogen from? There's many molecules, but of course, the best one would be water, because 2/3 of the planet are covered in water. The key aspect here is that that's an exothermic reaction. So breaking up a water molecule takes more energy than when you get back when you combust a hydrogen molecule. So you need something to compensate for that differential, and that differential comes from the sun, right? And so that's what we're doing. Different generations of quantum dots as sensitizers in this kind of photoelectrochemical cell in which we don't transform solar radiation into electricity, but rather we use it to break up water molecules. So in this case here, you can see a core shell architecture with a core of lead sulfide or lead selenide, a shell of cadmium sulfide or cadmium selenide. By varying the relative size of core and shell and the composition, you can actually tune the energy levels. Here we obtain fairly high values, 11 milliamps per square centimeter of photocurrent density and 110 milliliters per square centimeters per day of hydrogen generation. Of course, there's an issue here, you'll see it. Lead and cadmium are toxic elements, so they're not that great for the environment. So that was our first generation of dots. We went to a second generation in which they're made of copper indium sulfide selenide, greener process and not nearly as toxic elements. And of course, there's a trade-off. So from a photocurrent density of 11, you drop down to about 3 milliamps per square centimeter. So there's always going to be a trade-off. The latest generation of dots are carbon dots. So they're made mostly of carbon with a little bit of nitrogen, oxygen, and hydrogen. These are the 4 most abundant elements on the planet. So in terms of sustainability and sort of limited toxicity, that's so far the best case scenario. Yet another technology that we work on, this is for direct conversion into electricity, are solar windows. Now, if you want to power your building with solar windows, you can't use traditional silicon panels because they're not transparent. So if you place them in front of your window, you're going to block the sunlight coming in. That won't work. So basically what we're doing here is we have an organic matrix that is placed in front of the window, and then all around the organic matrix there are some very small silicon solar cells at the edges. So you can actually use much less area of silicon solar cells than having large panels. So it's going to be much cheaper. Now in the organic matrix, you have to place antennas. These are entities that will acquire absorb a photon at one wavelength and re-emit it at a different wavelength. And then the re-emitted photon can bounce through the organic matrix until it hits the cell. So most of the light goes in, and a portion of it is going to be refocalized on the silicon solar cells at the edges. If you have a large building with lots of windows, then you can actually generate a lot of power. The challenge here, the key challenge is the Stokes shift, which is the difference in wavelength from absorption and re-emission. If it's too small, a lot of re-emitted photons are going to be reabsorbed by another quantum dot. In our case, the antennas are quantum dots. So again, we use core shell architectures all the way to copper indium sulfide selenide, all the way to carbon dots. And essentially, that's the latest generation technology. Carbon dots, very inexpensive, and can actually channel quite a bit of power by using this concept of solar windows. So, conclusions and outlook. I hope I've shared with you our enthusiasm with nanostructured materials, studying the new properties that arise from size reduction, quantum size effects, surface to volume ratio, and so on. Clean renewable energy is central to sustainable development. It's one of the 17 Sustainable Development Goals. It's what our UNESCO chair is based on, the idea of capacity building in renewable energy technologies, and trying to deploy this in countries where there's actually no access to power, to electricity, water, etc. Addressing the energy challenge, we work on a number of different technologies. I didn't really have time to talk about this one. It's a little bit of a niche. But essentially, we've looked at dye-sensitized solar cells. Again, not much time to talk about it, mostly focusing on stability. Hydrogen generation using quantum dots, solar windows. And recall what I said. Through the UNESCO chair, we want to make a difference in terms of informing policy decisions. But policy decisions clearly depend on elected leadership. So I'm going to be a little bit controversial. This is not what elected leadership should look like, in my view, in my modest opinion. And this is what real-world leaders look like, in my opinion. This is the next generation. They're already giving us a tremendous example that nobody is too small to make a difference. These are the people who will most suffer from the choices we've made in our lifetimes, and they deserve all our support and all our respect. And I want to leave you with one thought. I guess you would probably all agree with me that we're facing an energy crisis. Now, crisis typically has a negative connotation in English. But it comes from Greek, and it actually means a choice, a divergence of paths. In its original meaning, it does not have that negative connotation that we always give it. So I asked a Chinese colleague, how do you say crisis in Chinese, and how do you write it? And I can't pronounce it, but this is how you write it. So it's a composite character, right? And the first one means danger, and the second one means opportunity. So after many generations of overexploiting the resources of the planet, we're facing imminent danger, but this could be a wake-up call, the wake-up call we really need, the opportunity we need to take to actually go back to a sustainable lifestyle on this planet. Thank you.
Thank you very much for your comprehensive and impact on the list that we have to do. So I wonder if there are space for the group for questions.
Just a comment on the question. Being the editor of Renewable Energy Journal, I would like to just mention to this audience that renewables are much higher value than the 1% claim. Of course, doesn't reduce the magnitude or the importance of your work, but the real figure is around 10% nowadays. Yeah. And in electricity, generally, and electricity production only, it's about 25%, out of which half of it is just from hydrogen. Yeah. You have to put it in the right perspective.
Yeah.
You speak about 1% with this.
1% is only solar. Yeah, so hydroelectric is 2%, and the biomass and other, which are all the renewables, is about 13%. So maybe 2%. Sure, but it's, I mean, I agree with you, but what I'm trying to say is that we're trying to bridge this gap here, right? It's still huge. I mean, I mean, our estimates are probably not that far off, but the gap we need to bridge is still huge. But fair enough.
Any other questions?
Over there.
Okay.
You said I was optimistic.
Yes.
My question is, are you optimistic or pessimistic about the future of energy?
Well, that's $1 million question. Next question? No. I would like to be optimistic. The problem, again, goes to elected leadership. The problem goes towards the imperfections of democracy that we've observed. In my view, democracy only works if people are educated and informed. And if they're not, they can be manipulated. So, you know, the problem is not Donald Trump in the US. It's the 80 million people who voted him and who support him. And those people, I feel sorry for them because they're being manipulated, right? It's not even their fault. They're just easy targets for manipulation from Fox News and other stuff. Same thing about Brexit. I mean, Brexit, maybe there was a slight majority of people who wanted to move out of the EU, but at the end of the day, within that majority, I don't think they would agree on a soft Brexit, on a hard Brexit, on a hard-boiled egg Brexit. So at the end of the day, what are we looking at? That's the failure of democracy. And, you know, democracy is key because there are some reforms, like education and energy, whose results you only see over 20, 25 years. But those people, they just want to be reelected over 4 or 5 years. So they don't care about something that's going to happen in such a long term, right? It's not relevant to their livelihood. Yes?
Yeah, but don't you just make the culprit on the West? And we have Russia, China.
Absolutely.
Democracy is still the best of the world.
Yeah, I fully agree with you. That's why I'm European.
I agree with you that there's no doubt about that. But even if you take China and India, that are huge polluters, they belong to that category of developing countries, and they've developed quite rapidly. And how do they develop? By using fossil fuels. They only want the kind of lifestyle we have, right? Can we blame them?
So we are optimistic.
Let's be optimistic.